You guys still see my screen? The Zoom thing went away.
Oh, yeah.
Okay, cool. Okay, so today we're going to talk about upgrading the parser. So if you guys remember last week when I tried to demonstrate the parser, there were a whole lot of things that were going wrong with like variable names that started with the same letters as reserved words. Other stuff like that. So like when we had a variable name that started with F, it was a problem because false is a reserved word. When we had a variable name that started with L, it was a problem, et cetera, et cetera. So Parsec is actually designed for parsing languages. And so it has a whole bunch of tools to like help solve these problems for us. We could solve them ourselves, but like, why reinvent the wheel? So we need a couple more Parsec modules. So the first one is called language. Hey, look, that name seems like it should be relevant. And then the other one is called token, and I'm going to import it qualified because it exports a bunch of names like parens and braces and stuff like that, which are combinators that take a parser and then return a new parser that parses the same thing but surrounded by parentheses. And that's very useful, but the name that it exports has the wrong type, and I'll show you what that means in a second. So I want to redefine it in the useful way so that it has the correct type. Okay, and then there's one other thing. Have I talked about record syntax for data types yet in these workshops? If anybody doesn't know what that is, speak up and say so, and then I will just introduce it, and we'll start there.
Well, I don't know if anyone's going to speak up, but you haven't introduced it, so
okay.
Like lots of people don't know.
Okay, so we'll start there. So the kinds of data types that we've talked about so far are introduced with the data keyword like this. So like you could say, color equals red or blue or green or whatever, stuff like this. This is fine. We've also talked about being able to contain values. So like, for example, here, the just case contains something of type A. And this is fine when you have types that you're going to pattern match on a lot. So you can extract that A with pattern matching, and just kind of generally for types that don't contain a lot of data. But say you have a type that contains a lot of data, right? Like a document, like you're making a page or something. What you can do is you can make what's called a record. And so the syntax for that looks like this, or we'll do it this way. And so now in the braces, you can put a whole bunch of fields and specify their type. So I can say title, probably a string, author, probably also a string, date, maybe I have a date type, and then, there's body, and then maybe this is, like its own type, document body. And it's complaining because these don't have definitions, but that's fine. So this is called a record. And now it has a bunch of named fields. And so when you give a named field like this, Haskell will automatically give you what are called accessor functions. So if you look at the bottom here, where it's showing the type of the thing that I'm hovering over, it says title is a function with type document to string. So the field has type string. The accessor function takes a document as an argument and returns the title field. Okay, so it's a way of extracting information from your document, or just generally from your record. The other thing that you get is this thing called record update syntax. So say I wanted to have a function that modified the title, right? So it took a new string, let's say. So the string is going to be our new title. We take a document as an argument, we return a new document. So this is new title. D, we get this thing called record update syntax. So I can say title equals new title in these braces, so D is a document. And then the braces immediately after D say modify D so that now the title is the new title instead. And this doesn't do an in-place modification of D because everything in Haskell is immutable and this doesn't change that. Instead, it's like a function. It returns a new document with a different title from the old one. Okay, does that make sense to everybody? If any part of that is confusing, Sorry, if I open the thumbnail thing on the side, can you guys see this? I can keep it closed if it's.
No, we can't.
Oh, you can't see that. Okay, cool. Okay. All right, so it doesn't sound like there's any confusion, so I'm going to get this out of the way. The reason I bring that up is not because we need to define our own record type. Ooh, whoops. I should get rid of this too. It's because the Parsec module that we're using defines a record type, and we need to make use of it. So the record type that it defines is called language def. So we're going to create our own thing, the PicoML def. And this is a language def. And language def takes a type argument that doesn't do anything, so just ignore that. And so what we want to do is we want to take the default definition, which is called empty def, and we want to modify a bunch of its fields for our own purposes. So the default definition does like reasonable things for identifier names, like they have to start with an underscore or an alphabetic character, and then everything after that is either an underscore or an alphanumeric character. That's reasonable. That's basically what you'd expect from a programming language. It has reasonable definitions of what characters are allowed in symbols, like operators. Stuff like that. It's case sensitive by default. You can turn that off in Parsec. So we want all of the like normal defaults, but we want to change a few things. So in the reference code, I changed the syntax of comments, but actually I think that doesn't matter, so I'm not going to talk about it. Okay, so first of all, we have a couple of reserved operators. The equal sign is reserved by the let syntax. And then the double semicolon is reserved for ending statements. And we have a bunch of reserved names. So not reserved operator names, but just regular old reserved names. Whoops, don't do that. And so these are all the things that were causing problems last week. So true and false are our reserved Booleans. Let is reserved. And then today we're, Today we're also going to add if, then, and else. And if you've never seen this way of laying out a list before, this is standard in Haskell. You separate things, you put the commas at the start of the line, and then the lines are like kind of grouped by what they do. This is just organizational for me. So the first line is the reserved Boolean names. This line will be for things that are reserved by let. So right now this is just let, but the word in will also be reserved later. And then these are reserved for conditionals. So, okay, this is our PicoML def. This is all we need. And now what we want Parsec to do is we want Parsec to give us a parser that will parse the tokens of our language. So tokens are things like variable names, literals, keywords, etc. So now we get ourselves a token parser, and I need this T in front here because this came from the module that I imported qualified. And it also takes a type argument that doesn't do anything. And I just ask it to make a token parser using the language definition. So, okay. So now, the problem that I mentioned earlier is like with things having the wrong types is token parser is actually a record type, and it contains parsers for all of the tokens of the language that it knows how to parse internally. But the problem is that the accessor functions want a token parser as their first argument, and it's inconvenient to pass PicoML around everywhere. So what I want to do is I want to write parsers like this. So I want to write my own definition of, for example, lexeme, which is defined as access the lexeme parser from PicoML. And now I don't need to refer to PicoML whenever I want to use the lexeme parser. The lexeme parser just parses a thing and then parses all of the whitespace after the thing as well. So it like throws away excess whitespace. That was another thing that we talked about last week. Our parser didn't know how to deal with whitespace properly. So I'm just going to define a bunch of these that I need. There's nothing too interesting going on here, but like have to do this that I can actually write code that works. So I want parens, I want brackets. Okay, so those are the simple combinators. Then I want a couple that can just parse tokens but aren't combinators. So one that parses identifiers, one that parses string literals. If you guys remember, we wrote our own string literal parser a couple weeks ago as like a side thing just to show how to do it. When you're using Parsec, you actually don't need to do that yourself. Parsec can do it for you. So I was mostly just showing it as like an interesting thing because we weren't doing anything else that week. Okay, just 3 more. So then these ones, reserved and reserved op, they take the name of a reserved keyword or reserved operator as an argument, and they parse that name, but they also make sure that it isn't followed by something else that would have made it a regular legal identifier or legal operator instead. So like, for example, the variable name letter, L-E-T-T-E-R, starts with the reserved word let. So if you tried to use the reserved word, like the reserved parser, reserved let to parse that, it would reject it because even though it starts with the right 3 characters, it's followed by something that isn't whitespace. So that's another thing that got us last week that Parsec is now just going to solve for us. Okay, and then the last thing that I want is a parser that parses whitespace. And I'm only going to use that once. So, okay. Oh, what are you upset about? Oh, it's probably needs a type signature. Fine. Okay. Was that the problem? Oh, no, that's the problem. Okay. I want mine to be all lowercase because I prefer that, but all right. Okay. So now, ooh, my diff that I'm looking at on my other screen is a little wrong. Okay, that's okay. I know that this is supposed to change. So before, let's see, when we only have parse statement here, because the lexeme parsers throw away whitespace after the tokens and not before, that means if we don't parse whitespace before this statement, then if the string starts with a space, we're going to reject it. And that's obviously wrong, right? That's not good. The other thing is, what if the string is more than one statement, right? What if it's like some statement and then a double semicolon and then more stuff? Our interpreter doesn't support doing that. It only supports one statement on a line, but it won't reject that. It'll just parse the first statement, say good, and then throw away everything after that. And that's bad. So what we want to do is we want to make sure that we start by parsing whitespace. And then we want to parse a statement. And then we want to parse an end of file. And what these operators mean is they mean do the thing on the left, then do the thing on the right, but return the result of the side that the arrow is pointing towards. So in this case, we parse whitespace, but then throw the result of that away and parse this whole thing. And then this whole thing says parse a statement, and then parse an end of file, but return the result of the statement. So this is a kind of common idiom. I showed the between combinator, I think, a couple of weeks ago. This is like another way of doing the same thing. So you could take your pick of whichever one you think looks nicer. So, okay, now that we have these new token parsers, we can start doing some nicer things. Like here we have a reference to string double semicolon. Well, now we can use reserved op. So same thing I was talking about earlier, it'll make sure that it actually is the reserved operator double semicolon. Let's see. We can do let statement a little bit nicer because we don't need this explicit spaces anymore, or the ones on this line. So instead of doing try string let, which was our way of trying to solve one of these problems, now we just use reserved. Instead of using parse name, we use parse identifier, or not parse identifier, it's just identifier. Instead of doing this whole thing, like between spaces, we just do reserved op. And then the parse x part is the same. Oh, yeah. And then this needs to be a string literal, not a character literal. Okay. So it just kind of, we can keep doing this to make each of our parsers better. We don't need this name parser anymore because we have identifier now. So down in parse var, we can change this to identifier. Here, where we have string, we can change this to reserved. And then this one is actually a little bit different. So this one parses unit. And the way that this is written right now, it requires you to have the parentheses with no spaces between them. But there's no reason that we actually need to enforce that. So the other way that we could write this, is we can say, use the combinator that wraps things in parens, and then just wrap the parser that doesn't parse anything. So this will succeed whenever you have just one parent followed by another with any number of spaces in between. And that's the normal syntax. If you go to a Haskell terminal and type an open parenthesis and then 20 spaces and a closed parenthesis, it'll give you unit. So this is expected behavior. Another thing that we can do is we can add another case to parsecs. So an expression might be parens surrounding another expression, for example. And so the new token combinators just make that super duper easy. And then the last thing is the token parsers do actually have some parsers for numbers, but we're going to keep using the one that we wrote instead because Parsec's token parsers don't do this thing. So we did this special thing with our own float parser so that you can write 0.5 instead of 0.5. And Parsec's token parsers won't allow that, and forcing them to allow that is actually more complicated than just doing this ourselves. So we're going to leave our own version of this. And then we can get rid of the string parser that we wrote and use parsecs instead. So in order to do that, I need, oh wait, actually, instead of deleting that whole thing, I can just delete this part. And then change to end of line and use string literal. No? Come on, yeah, okay, there we go. So now all those problems that we were having with the parser before, I just wrote some code for 20 minutes and now they're all gone. So we don't have to deal with any of those problems anymore. We can pretend they don't exist. The other reason that doing this is a good thing is because once we start adding operators, we're going to have to deal with the fact that operators have precedence and they have associativity. And that's complicated. But even worse is that a lot of the time when you're writing parsers, you end up with what's called a left recursive grammar. And so I think most of you said you've taken 374 or at least have seen grammars before. So when you have a grammar production where, say, I'll just put this in a comment, say you have a rule that says the non-terminal A turns into A followed by some random characters. It doesn't matter what these are. They can be any terminals or non-terminals. Normally, like in the theory of grammars, this is fine, right? This makes perfect sense. It just means you end up with a list of these things. But for a recursive descent parser, this is actually a big problem because for a recursive descent parser, which is what we're writing, this means that in order to parse A, you need to first parse A. And so you immediately run into an infinite loop. And so when this happens when you're parsing expressions with operators, that's a big problem. And so Parsec, again, gives you a way around this, but using it is a lot easier if you've done all of the stuff that we just did already. So I'm not going to talk about that again when it comes up. I'm just going to use the powerful stuff for operators and pretend that it was never a problem. So, okay, if anybody has any questions about that, now's a good time.
In the chat, there's a question.
Yeah, I see.
Okay.
Is it easier to make operators using prefix notation? So if you use prefix notation, precedence and associativity stop being problems, but the code gets a lot harder to read. And part of the point of what we're doing, is to show how to write the kind of language that you would see nowadays. If you were writing, say, Scheme or Lisp, then yeah, that would work. Although Scheme and Lisp have a lot more parentheses in addition to the reverse Polish notation, and the parentheses actually help make it more readable. Just trying to read straight reverse Polish without the parentheses is really hard. So if you've seen Lisp, you might think that the parentheses are hard to read, but if they weren't there, it would actually be even worse. So yeah, okay. So the other thing that we were going to do today, because I knew that wouldn't take an hour, is implement conditionals looking at the clock, I can already see that this isn't going to take 30 minutes. So I'm gonna probably start going a lot slower. And if anybody has any questions, please just interrupt me. Okay, so I want to add a case to our expressions, and actually I'll put it after var. So we're going to add a new expression type called an if expression. And all it has is 3 sub-expressions. So this is what we call the condition. So you say if condition, then true case, else false case, false case. This is the true case, this is a false case. So now I guess we can write the parser for that first and then talk about semantics. So let's see. Yeah, okay. So over here, we want to add a new thing for parse if. Should that be parse if x? Now I have to look at my code. No, just parse if. Okay. Now we write a parser for if expression. So this parser returns an expression. And how do we parse an if expression? Okay, so we start by looking for the reserved word if. And then well, I'm just going to call these E1, E2, and E3. You could give them more descriptive names if you wanted, but so we parse an expression, that's the condition. And now we look for the reserved word then. And then we parse another expression. So now this is the true case. And then the reserved word, oops. Wow, typing is hard. There we go. Else. And then the false case. And now we have all the pieces that we need, and we return if x condition true, false. Okay, so that's the whole parser. And now we don't have to deal with spaces. We don't have to worry about variable names that start with the 2 letters if, but then aren't actually an if, et cetera, et cetera. So just all of these things are no longer even considerations. It's great. Okay, so the next thing to do is type checking. So I'm going to make a new line here, but before we can write the type checker, we need to know what the semantics are. So let's go over here to the wonderful semantics PDF, and let me zoom in on that a little bit. Okay, so since last week, there are 3 new rules here. Let's use green. So this rule is new, and these 2 rules are new. So the if rule is super easy. The condition has to be a Boolean. Ooh, whoops, that looks terrible. Let me actually change the color. So the condition has to be a Boolean. It's not allowed to be any type. The true and the false case can be any type as long as they're the same type, right? So here, this tau and this tau have to be the same. But other than that, there's no restrictions. And then the overall type of the if expression is whatever the type of the cases were, right? Whichever case gets executed, the type that it returns is going to be the overall type of the if expression. It's actually 3:30. So if your commitment's at 4:30, it's not 4:30. But
is it a different time zone?
Possibly. Okay.
I don't know.
Daylight savings, maybe, I don't know.
Okay, anyway, so let's start with the type checking rule. So, oh wait, I need to get out of drawing mode. Okay, there we go. So let's see, can I put this over here and then bring this up on the side? And then get rid of the drawings because they're in the wrong place. There we go. All right, look at that, that's great, okay. So we want to type check if expressions in the environment gamma. Okay, so what does this say we should do? So it says first we should check that E1 is a bool. So actually what I'm going to do is I'm going to take advantage of Haskell's laziness, or at least a little bit of advantage. So I think I spoke about do notation before. Do notation lets you do things in sequence, and what in sequence means changes depending on what the return type is. So in this case, it's maybe. In sequence means that if any of these individual calls fails, like the type checking fails for whatever reason, then the whole do expression will just fail immediately, and I don't have to worry about manually pattern matching on just or nothing everywhere. So here I want to type check the second expression, same environment, like the semantic says. Type check the third thing. Okay, and now I want to check that the first type is bool and that tau1 and tau2 agree. So I want to inspect T1, and I want to check that it is the Boolean type. And if it is, so you can use guards inside of case syntax. I've talked about guards before. If it is, I want to check that tau1 and tau2 are equal. And if they are, then I can just pick one of them to return. It doesn't matter which one I return because they're equal. And if they're not equal, we return nothing. So type checking fails. Okay, so if they are equal, then type checking succeeds, returning tau1. If they're not, it fails. And so just, whoops, bringing up the draw again, using more pretty colors. So we have this part is the first line. That was terrible, but okay, that was better. And this one, yeah, there we go. Okay, I made a mess of that, but you know. Okay, so we have our 3 recursive calls. Let me just clean that up a little bit. Okay, and then we check that this is actually bool, and then we check that these things are actually equal. Okay, so again, the code comes straight from the semantics. Does anybody have any questions about that? That's literally the whole type checking rule. Like we're done with the type checking now. Okay, doesn't seem like it. So now we come down here to evaluate, and we have to do the same thing, but now we're adding a new case for evaluation. And if you look at the semantic on the left, which I'll talk about in a second, you'll see that there's actually 3 rules instead of 2. So let me just say that this is undefined. Okay. Or sorry, there's 2 rules instead of 1. I don't know what I was saying. So the first rule is called if1. The second rule is called if2. And you'll see there are only 2 differences. So the first difference is in one rule, this is true and this is false. And then in the first rule, we evaluate E2, and in the second rule, we evaluate E3. So these are the only differences. The reason that you have to express this as 2 separate rules is because semantics rules don't have a way to express a condition in one rule. So like there's no way to say like, if this is true, do E2, if it's false, do E3 in one rule. So we use 2 separate rules to express this, even though they're talking about the semantics of the same expression type. And so all this means is that before we can decide whether we have to evaluate E2 or E3, we're going to have to check which one of these is true or false. I think last week I spoke about Haskell's laziness, where Haskell won't actually evaluate something until you know that it's needed. You could take advantage of that here to just evaluate all 3 things in one go and then pick which value you actually care about. But because of some stuff that we're going to do in the near future, probably next week, or maybe not next week, when we add exceptions to the language, that won't work anymore, because once we add exceptions to the language, then we're going to need to tell Haskell like, hey, you need to like actually do these things in order. And then if evaluating the expression that isn't needed would have caused an error, then we're actually going to get an error, and that would be a problem. So instead of leaving that for later, we're just going to not run into that problem at all. So first we want to evaluate E1. If it's true, we're going to evaluate E2. That's what the rule says. And then the rule also says, coming over here, that whatever the result of evaluating E2 was is the result of the whole if expression. That should be the expected behavior, right? You know how if statements behave in regular programming languages for the most part. The difference, of course, is that we're not allowed to have no else case. So if expressions actually always do return something, that's not the case in every programming language. Okay, and if it's false, we evaluate E3. And that's the whole rule. So there's nothing else to do there. Let me clear these drawings. Does anybody have any questions about any of that? Doesn't seem like it. Okay. So anyway, that should be everything. We should be able to load this up into a REPL now. Ooh, I cannot move that window because all of the Zoom stuff is in the way. Come on. Nope.
Can
There we go.
Windows left
Got it.
arrow over.
Yeah. No, I had to like do the Control-Alt-Shift-H thing to hide the Zoom toolbar, and then like, yeah, all of the stuff that you guys can't see was in the way of the top line, so I couldn't move it. Anyway, so I can load up this file. And launch main. And so now we have our REPL, and so I can do all the things that I can do before. I can say, 5 hello world, blah, blah, blah. But now I can also use variable names that start with the same things as reserved words. So I can do this, and this actually works. So last week that was causing problems. The other thing I noticed while I was preparing for this week is that I forgot to do character constants. So since we have some extra time today, I might as well just like throw those in there. It's very easy. But like, I don't need to talk about that. That's super simple. If you want to do that as an exercise, you could. The other thing that we can do now is we can say if. So I can say if true, then, I don't know, hi, else, bye. Right? And so that works like you would expect. I can say if false, the same thing, we'll get the other case. We don't really have interesting ways of generating Booleans yet because we don't have function calls or the kinds of operators that could generate Booleans, but we'll get there soon. And like once we have all of the other stuff that we need in place, adding those kinds of things is going to be really easy. Like it'll mostly be a parsing exercise, and the semantics are actually easier than parsing them. But yeah, so now we have all these cool features. I can actually use a variable named foo. That was causing a problem last week. So yeah, any questions about this? Oh, I guess I can show the other thing. So if the condition isn't a Boolean, we're going to get, oh, parse error is not what I was expecting. Interesting. That's my fault. When I was upgrading the parser, I forgot something that I did. Yeah, okay. So remember earlier I said Lexeme parses all of the white space after a thing. I said my diff was messed up and it didn't highlight this, but this is important. So now this will make it so that whenever you parse a number, the parse number parser also throws away all the white space after it. That's really important. So that's what was going wrong here. So I can reload that and try that again. No, then 0, else 1. Okay, there we go. So now it doesn't type check because unit is not a Boolean. So that's expected. If I put a number there, then it also won't type check because numbers aren't Booleans. If it's a Boolean, but these things disagree in their type, so one is a number, the other is unit, it also won't type check. And these error messages are completely unhelpful and they don't actually tell you what went wrong. So I think what we'll do in the future is we'll talk about how you would fix that, but then I'll probably leave it as an exercise because it doesn't actually require changing all that much code. It's just when things go wrong, instead of returning nothing, you return something else along with an error message. Actually, I have time. I could talk about that now. What do you think, Reed?
Sure.
Okay, sure. Let's do that. Unless anybody else has something else that they'd rather talk about or they have a question. Eyes wide. Okay. Okay. Yeah, sure. So let's do that. So, okay, I'm going to need to talk about one of the other Haskell types. So if you look at our 3 type checking rules here, So far, what we've been doing to represent failure is just returning nothing. So we have this maybe type. In fact, I have a REPL here. I can even pull it up. Oh, that was a lot more information than I wanted. Okay, only the first line matters. So we have this maybe type, which is either nothing or just. So nothing is a failure case, but it doesn't tell you anything about what went wrong. There's another type that people use frequently to include information about what actually went wrong, and it's called either. So again, only the first line matters. Let me highlight that. So this time there's two type parameters, and you have either A or B, and the constructors are called left and right. Those are just kind of random names. They could really have been anything. Mathematically, the names that people use are P and Q, but like that's kind of dumb. In a programming language, that doesn't really tell you anything about what's going on. So people don't use that. And so the normal way to use either is that the type variable A would be your error type. So whatever kind of message you want to include when something goes wrong. And then B is your success case. So right is kind of like just, and left is like nothing, but with more information. So instead of returning maybe type, I think our error messages can just be strings here. Like there's nothing too interesting to do. So instead of returning maybe type, we'll return either a string or a type. Instead of just, we have to return right. I'll come back and fix this one in a minute because there's a little bit more to talk about. Here, now, these two things are kind of different. So now if the first thing is a Boolean, or actually, no, I guess not. Okay. So if the first thing is a Boolean, but these things aren't equal, then we need some kind of error message to describe the cases. So I'm just going to say left cases of if have different types. You could use any descriptive error message that you wanted. Also, we need to replace this just with a right. And then here, we need an error message for this. So in this case, what went wrong is that the condition wasn't a Boolean. So now I'll say condition of if is not a bool. Okay. And so now you can see my editor is still highlighting this thing red. There's still a problem here. So the problem here is that lookup returns maybe. So in this case, we need to unwrap the maybe and then replace it with our new success or failure type. So if it succeeded, then we have some type, and we just want to replace that with a right instead of a just. If it failed, we need an error message. So I'll ask, I guess, who knows what causes failure here? What programming error causes type checking to fail this way? So the error is you go to look up the name in the typing environment and it's not there. Anyone have a guess? Okay, awkward silence.
Undefined error.
What?
Undefined.
Yeah, so this happens if you try and refer to a name that you haven't actually defined anything, right? So this is like variable is not in scope.
Okay.
Yeah, so undefined is the right idea. So we'll do exactly that. We'll say variable name not in scope, and then the name. And remember that this is a type checking error. So this happens before we even go to evaluate the thing, which is good. So if a programmer makes this kind of mistake, they try and refer to a variable that's not in scope, we don't start executing a whole bunch of instructions before we realize that we weren't supposed to do that, right? We just run into a problem immediately. Whoops, come on. Okay, so now we just have a bunch of new problems down here because we're using a different type. So in this case, I'm going to say, actually, okay, let's do this. So in the case that we get a string here, that will describe what went wrong. So if this is an error, we just want to propagate that. If this is a success, we want to propagate that as well. And so I think that should be all I have to do is just, come on, replace nothing with left error everywhere and then just with right. And then there's going to be one more problem lower down in REPL pretty because it's expecting maybe instead of either. And so we'll have to fix that too. You need to be indented a little more. Here we go. Okay. Yep, so that's all of those. Now this needs to be either string or result. If we have a message here, oh, whoops, I need parentheses. Okay. If we have a message here, then there's no reason to output this useless garbage. Whoops, what's the, no. Oh, okay. I guess Emacs doesn't know about double quotes being matching. Okay. We just output the message itself, right? There's no reason to have that meaningless did not type check thing. If we have a success case, then we do the same thing that we did before. The types here don't agree anymore, so I have to fix that. And then same thing here. So this needs to be, let's see, I'm just gonna write it this way. So I've shown this syntax before. Or wait, actually, that won't even work. Okay, I'm not going to explain why, but the compiler is not going to like it if I do that. So we'll just do this. If I remember, I'll talk about why the compiler wouldn't have liked that when we implement the same rule in our own language, because we're going to have the same problem. But okay, so now everything should agree. Yep. So I can reload this. Okay, and so now if I start doing those same things that were causing problems, so now it'll say condition of if is not a bool. If I make it a bool but make this mistake, cases of if have different types. If you wanted a more meaningful error, you could, say couldn't match expected type probably number with actual type unit, however you want to make that error. Our type checking system is going to get a little bit more involved next week. And so as that happens, I might actually just kind of make that change incidentally because it's going to be easy. But yeah, so all of this stuff, if you try and refer to a name that's not bound, variable name not in scope, instead of just did not type check. And that's like a more meaningful message too, right? Like if you type a variable that was out of scope and the message just said did not type check, well, that's really useless. So yeah, now we have slightly better error messages for type errors. Yeah. The other thing that I wanted to explain, just since I have a few more minutes, was, let's see, where did I do it? Yeah, over here. Notice that when I was type checking the if expressions, I used do notation, and originally the do returned a maybe. And that just worked. And then I just changed the maybe to either, and I didn't change anything about the do block. I mean, other than the stuff all the way down here, but that was for a different reason. And it still just works, right? It does the thing that I want it to do. And so I think next week we're going to get into a little bit more depth about what exactly is happening there. But the idea is that the idea of sequencing for both maybe and either are very similar. You propagate nothings for maybe and you propagate errors for either. But when there's a success case, you take it out, bind it to the name on the left of the arrow, and then keep going. And so as we do more work with the type checker, especially, we're actually going to want to add some more things on top of this that have slightly modified notions of what sequencing means. And you'll see that it's much, much easier when you have do blocks and the underlying machinery to help you with that than when you're doing it yourself, like we did all the way down here, where we have to like manually thread the environments through the calls to REPL. But yeah, does anybody have any other questions about what we did today? Any confusion? We talked about parsing, implementing conditionals and the semantics for those, and then briefly about better error messages and the notion of sequencing. Okay, it doesn't seem like there's any questions. I pushed the reference code for today right before I started. That was one of the things that I needed to set up. So feel free to poke around at that. If you have any questions, then just ask in Slack.
Okay, cool. And then will you post this new updated with the error messages code, or?
Oh, I did not do that, but I can. Let's see. Yeah, okay, let's just copy what I just